Hello, and welcome back to the Nanoscope. Here we continue our journey through enlightened science to see what has become of modern atomic theory, see where it came from. Now, this episode, instead of traveling around in my brother's time machine in real time, I've spliced together bits and pieces of different interviews with different chemists from ancient history to see how much we can fit into one episode. Let's get going. And remember, our current thought of what the atomic model is just little spheres floating around in space. So, Mr. Mendeleev, you discovered the elements were periodic according to weight. Can you tell me a little bit about what that means? Yes. Well, you see, when you weigh the atoms, you can sort of sort them by their weight, and you begin to notice that there are properties. There are properties the elements have that carry periodically. Every time you go this many steps, this many jumps of weight, then you see these same properties again. And if you arrange them into a sort of periodic table, you can see which one has these properties by where they end up and which row they are in. Of course, none of this would be possible if we didn't have the sort of exact weights of the elements. I believe it was a gentleman by the name of Amedio Avogadro who sort of pieced together what the exact weights were, and it all builds on itself. Thank you, Dmitri Mendeleev. Now, William Crookes, you had a cathode ray tube. What is that? Can you talk to me a little bit? All right. This is a bit of a long one. It's like a glass tube, and all the air has been emptied out of it. We sort of got better and better at removing all the air from inside of a tube, creating a vacuum, see? And when you create a vacuum and you put a cathode and an anode, so two charged plates, sort of weird lines start to appear. And if your cathode is a solid plate and your anode has a hole in it, you can actually see this eerie green glowing line appear that sort of goes through the anode hole to the other end of the tube. And I really wanted to know, what is that? And it all sort of went back to this theory that everything was made up of particles, and I thought, is this what that is? Is this those particles, these little charged little balls that would bounce around in space? And so I put a little blockage in the tube, and sure enough, there was like a shadow cast as if the particles were hitting the wall, and then I put a tiny, almost like a water wheel in there, and it began to spin as if particles were hitting it. It was incredible. But you really ought to talk to J.J. Thomson. He knows a lot more about this than me. He sort of took off with the cathode ray, so I'll set you up with him. Well, thank you, William Crookes. And now, listeners, an interview with J.J. Thomson, one of the big, important figures in atomic theory. Let's jump right in. Hello, welcome, Mr. Thomson. Now, I'm doing a little bit of research on this atomic theory, and I just like a quick interview. What can you tell me about the cathode ray experiment you did with William Crookes? Well, I suppose we'll start at the beginning. You see, Crookes and his little water wheel sort of pieced together that the eerie glow was particles, some kind of tiny stream of little spheres, much like what John Dalton suggested all matter was made up of. So I figured, if they're little particles, and they're reacting to charged plates, the cathode and anode, they're charged. They must be, negatively. So I used electric fields and other electrified plates. I held them up near the cathode, and I watched the line of green particles bend, and I knew I could figure out their charge based on that. I used the simple equation of deflection and found the charge of these tiny particles. About 1.6 times 10 to the negative 19 coulombs, one of the ways we measure charge here. Not sure where you're from. Anyway, that's not important. What's important is that no matter how long I left the cathode ray tube running, the little cathode didn't get any smaller. its mass was exactly the same, which meant that the particles that made up the cathode were not moving. The particles that made up its mass, anyway. So therefore, whatever little particles were flying through my ray tube were a part that made up the atoms of the cathode. That meant John Dalton wasn't quite exactly right. His little atoms could be devised. They could be split up into smaller parts. I called these smaller parts corpuscles, but they were renamed by other scientists, a much more fitting name. They are now called electrons, and they are a part of what makes up an atom. So, Mr. Thomson, this means that John Dalton's theory was wrong? His atoms could be devised? No, not necessarily that he was wrong, just that his theory needed to be rewritten a bit. So I proposed my own model for what the little atoms may have looked like. I call it the plum pudding model. So then, what did your atomic model look like? Well, it was like a big sphere, but the big sphere was, well, some tasty pudding, positively charged pudding, and in it floated the little corpuscles, the little electrons. They floated inside a positively charged field, so when not interacting with the atoms, they will remain neutral, but when interacting with magnetism or other charged particles, the little electrons will fly out of the pudding to whatever other place they can find. Now, Mr. Thomson, do you think you could repeat your experiment in my studio? Well, I could certainly try. Oh, that is the last time I ever let a chemist near an electrical outlet. Oh, let's just move on to the next bit. Alright, listeners, before we move on to our next interview, there are 3 quick names I'd like to mention who made the next jump in atomic theory possible. The first is Robert Brown, from much longer ago than the others, about 1827. Robert Brown wasn't a chemist, he was a botanist, and he noticed that dust particles in grain pollen floating in water jiggled around for no reason. Later on, Albert Einstein figured it must be the particles, the atoms in the water, bouncing against the grain. And in 1905, Albert Einstein came up with a mathematical equation to show how this movement might work. And it just goes to show more evidence that atomic theory, and therefore particle theory, are valid. And that just goes to show that science really is a group effort. We couldn't have had all these huge leaps in atomic theory without the help of others before them. Albert Einstein himself is more well known for the theory of relativity, not atomic theory. But that doesn't mean he didn't help out with the study of atomic theory. And the third name I would like to mention during this short break is Hans Geiger. Hans Geiger didn't really make any steps in what atomic theory was or what it could be, but he did have and discover one of its great applications, and those were alpha particles. Hans Geiger, along with other chemists, noticed that polonium, a newly discovered element, would radiate relatively large atomic particles. These particles would later be called alpha particles, and Hans Geiger built a device, aptly named the Geiger counter, that could detect alpha particles. This allowed chemists to learn more about alpha particles, and eventually to use them in experiments. One such experiment explored the true nature of what an atom really was. This takes us to our next interview with Ernest Rutherford and his gold foil experiment. Hello, Mr. Rutherford. Thank you for joining me in the studio today. Now, I've heard you conducted a gold foil experiment, and I'd like to hear a little bit about that. Ah, yes, the gold foil experiment. That must have been a while ago. Now, let's see if I can remember. I believe we wanted to test good old Joseph John Thomson's model, the pudding. Yes, I love me some pudding. Anyway, if we shot the alpha particles through some very thin gold foil, it should pass right on through it. These alpha particles, you see, compared to the electrons, these things were huge. They'd punch right through them. They'd fly through the pudding and they'd come out the other end. And mostly they did. But I noticed some of them deflected off in random directions. It didn't make any sense. So I decided to make an experiment out of it. We put up a screen that curved around the entire gold foil, and we noticed the angle of bounce was not like it was hitting some hard sphere, as John Dalton suggested, and ricocheting off. It was almost magnetic, as if there was something in the core of each atom that was positively charged and was repelling the alpha particles. So you're saying you discovered some hard little object in the center of each atom? Well, yes, that's what we thought. We called it a nucleus. And we thought, what if it wasn't some positively charged pudding? It was the nucleus. There's something in the center of each atom that holds that positive charge, that holds all the electrons to it. And so I made my own atomic model, called it the Rutherford model. Little bit egocentric, I know, but trust me. Well, then that begs the question. What did your atomic model look like? Well, I thought it was a positively charged field. Not some pudding, but a field created by a hard nucleus in the center. That hard nucleus, a little clump of positively charged little particles called protons. And around them swirled in a cloud the electrons. That's what the atom looked like to me. All right, then, really quick, Mr. Rutherford, my last question for you. We've heard a lot about the religious and sort of tie-ins to science of people's beliefs. What about you? Beliefs. Suppose after the Age of Enlightenment, people used that as an excuse for chemistry, an excuse for physics, an excuse to hide from the church. Suppose it was different. Some of us just did science for the sake of science, I guess. There was no belief necessary. We moved away from that as a society, I guess. Hope that answers your question. Thank you, Mr. Rutherford. Robert Millikan, author of the oil drop experiment. Can you tell me a little bit about that, Mr. Millikan? Absolutely. So, I started with little spray droplets of oil, and they fell through a little hole in this big, large plate. And as they fell down, I looked at them through a microscope, and I noticed, if I was very careful when I sprayed the mist, emulsified the oil, I guess you could say, I would know exactly how big those oil drops would be. I would know exactly their mass, the same, every single time. So then, I shot some X-rays between the two plates. This charged the particles. So then, when I cranked up the magnetism on both the upper plate and the lower plate, I could get the oil to hover in the air, exactly. And of course, from earlier, I knew its exact mass. And so, it was a simple matter of mathematics to find out what charge could possibly be acting on what mass inside those electrons of the atoms of the oil drop that could keep it suspended in midair against the force of gravity. You're gonna have to walk me through the math on that, Mr. Millikan. Oh, of course. So. The mass of the oil droplet was always the same. I could figure that out. And the force of gravity is always the same. So I knew exactly what force was acting on the oil droplet, pulling it down. But the magnetism holding it up was based on the charge of these little electrons and their mass. I knew their charge already because of Thomson's experiment where he deflected the electrons through a cathode ray tube. And so the only thing missing, if it was hovering, of course the effect of gravity, mass times gravity, would have to equal the attractive and repulsive force of the magnets. And I knew the charge. The only thing I didn't know was the mass of the charged particles. That was the only variable. So when I knew all the numbers, I just solved out the equation, and there it was. Thank you for the interview, Mr. Millikan.